people often confuse or misrepresent the connotation of deep learning in respect to with respect to machine learning and AI. Like umpteen times people use these definitions of these technologies interchangeably. So what I want from you right now is a description of what deep learning is and its relationship with AI and machine learning.
Oh, okay. I think the it's first of all just understanding the main difference between what is difference between AI, deep learning, machine learning. So AI is like a complete system which has this machine learning and deep learning algorithms in it. But it is an AI system will be like a full development system which will have other kind of pipelines or things. Whereas deep learning, they are like kind of an algorithms. Machine learning is also an algorithm kind of a things. And when you come to the difference between a deep learning and machine learning, it's like they say that machine learning is like a simple algorithm such as like the SVMs and stuffs. Now even a single layer perceptron is also accepted as a machine learning algorithm. And on the contrary, deep learning is like a multi-layer perceptrons are deep learning things. So yeah, that's a difference which people talk about.
I would like for you to go in a little bit more depth about how deep learning works, as in like probably talking about neural networks, how they are built, you know, probably talking about back propagation and how the iterations with different iterations, the model improves itself, and in general how to build a deep learning algorithm or a neural network framework.
Okay. So basically, to start with, there is this a basic problem which everyone tries to encounter, tries to solve, is the linear regression. So the whole ML models which are based, or the artificial neurons which are based, they are completely based on this problem to solve a linear regression problem. Okay, and on this we have built up various functions to solve this, various methodologies to map upon things. So getting to started with how do we build a neuron. So firstly, understanding what we try to solve. We try to solve a mapping problem kind of a thing, where we have a given input and we need to see that what exactly there could be a function f of x which will just map the given input to the given output, and we try to approximate that using a linear regression. So when we come to a machine learning algorithm, we first we see that how the algorithm tries to learn all of these things and get an estimated function value. When it comes to deep learning, the deep learning, we have something called as a perceptron. A perceptron is something which takes multiple single input or a multiple input, have a function f of x, which gives an output, which gives a prediction of an output, and this f of x is a black box which it tries to understand based on the given inputs or the given training data. So a simple algorithm will be feed in the input, the f of x learns upon it, and it tries to estimate the whole thing. And when it comes to deep learning, we have this multi-layer perceptrons. There are like multi-layers of these neurons which are just attached and connected in various formats and in a various manners, so that we are able to approximate f of x. So coming to the part that what is a backpropagation thing, backpropagation is like um, the given f of x is trying to update based on the so there's something known as a loss function. A loss function is something which tries to we try to optimize like a given function, our f of x, which we want to see what it exactly has to be optimized into. So here the backpropagation takes in picture, where it tries to take in the output of the earlier perceptrons in pictures to optimize the given function. Yeah.
What currently is the biggest pain point in regards to the development of these frameworks or in general just advancing this technology?
You mean the deep learning and stuff? I think like they are already at very par. They like this these technologies are very much came into the picture, and right now people are developing electronic circuits or trying to find out methods and how this could be made in a very sustainable way. And the other format is trying to understand the expressibility of the given AI models, of really understanding. It's like the uncertainty of the black box is very much not like what people don't want to understand. It's like, let's say you are in a medical field and you want to, like, okay, your AI model is performing well, but to understand, is it really performing the way it is? So to understand this AI thing is what the current field is. But with regards to the technology, the algorithms, we are way too ahead. We are way too ahead. And NVIDIA's QDNN was like one of the method, which, like, not method, I would say, one of the technology which enabled us to like take the exponential leap over here. So yeah, but with regards to that, it's we are way too ahead, I feel, and there is still more to come.
So probably then the next current advancement or studies being conducted in how to utilize this technology to advance some other technology like quantum computing, which currently is at a very developmental phase or a very rudimentary phase in regards to how applicable it is to solving actual real world problems. So I'd like for you to elaborate upon the utilization of deep learning and AI in regards to the development of quantum computing.
Okay. Uh, Regards to that, so basically, what we see is we use AI to understand some black box things, or some things which need to be computed very faster. So, quantum computers, when we say that it's not fully developed, it's all because of, theoretically it is we have understood a lot about it, but when it comes to a practical point of view, the circuit doesn't, like, the hardware doesn't support the way we want it, because of there are a lot of noises. And what we see is there are different methods of error mitigations and error corrections. So right now what researchers are doing is they're trying to put in AI to help in this, in terms of error mitigations, error corrections and stuff, and how it could just accelerate the whole thing, where we don't need to devise our own f of x. It's itself is trying to devise it by its own, and then it we can produce this model. One good paper, I would say, and this is by NVIDIA, which they have recently published, is a GQE, generative quantum eigensolver. This paper, they try to just have a generative circuits on how, and ansatz could be there, and that could be optimized very well on a quantum system. So as per what I have understood correctly, so that this is a one of a way you could see that how generative AI is taking in picture in quantum technologies, and it is helping the quantum computing to boost up. Because yeah, we can't actually right now, I myself am not able to visualize anything pure quantum. It's like there is a coexistence of classical and quantum. Even there's a recent paper by IBM, which a quantum centric supercomputing, which they have seen, which is also goes with regards of existence of classical and quantum, and the processing power of classical should match with the processing power of quantum. So that's how we will be working towards the utility of in this field, of how really quantum computing will be very helpful. Yeah. um,
Um, Also, what are the current challenges in integrating probably deep learning or the AI technology and quantum computing? Maybe this in regard to the scalability part. Like we know that there's a lot of noise and fidelity issues and decoherence, but like what is the true complexity of these hybrid models? Because you did talk about something very important, that currently we aren't able to develop fully or completely realize the potential of purely quantum systems. So we need the assistance of classical frameworks to sort of amalgamate a framework that has the essence of quantum and the support of classical. So what are the problems and challenges with that, and what are we doing to solve those?
Okay. With regards to when you say about integration of a deep learning and quantum, so there is like two aspects. One is like deep learning for quantum computing, and one is quantum deep learning, or let's say quantum AI. So let me first address the deep learning for quantum. I think which I had did address before, that how we are trying to be helpful in that, and that is the most of the research which is going. With regards to quantum AI, the main problem is the circuit depth. It's like even if we have an achievable qubits, the amount of quantum circuits which are required to understand the quantum neurons is very large. We can't just directly scale what we did on an artificial neural network to put directly on a quantum processor. It's like uh, it's like we are again trying to put a classical processing thing on a quantum processing unit, which is not how the way it should work with. There is a different math that should work in this regards. Like we want to harness the quantum power, the quantum speed up. So to harness this, there is a coexistence, which I believe is like there are particular ways in which a classical is faster, but then some certain aspects, like if we can put a data in a superposition, there's where a QPU can take place. So recently we had a talk from Sophia. She's from CERN. She's the head of this whole quantum technologies over there, and they she got a very good result over there at CERN using quantum AI. But then the major problem, which I think is discussable over here, is that the first of all, the number of qubits which we need to actually do a quantum AI, and over which the circuit depth is also crucial in this aspect. So having a good circuit depth with less error is is something which we want to achieve. And I think right now the IBM's roadmap is also towards achieving more towards this thing, rather than having n number of qubits.